All right. So let's dive into it. So this topic is all about entropy, which we're going to define in just a second. But to start things off, first, we're going to talk about how we've kind of recap a second law of thermodynamics. So in that unit, we talked about two statements of the second law of thermodynamics. One was the Kelvin-Planck statement, which applies to heat engines. And then the second statement that we had applied to refrigeration cycles. But it turns out that the second law also leads us to define, this should be leads us, to the definition of a new property, which is called entropy, which is the focus of this entire topic. And this property can be thought of as a measure of the microscopic disorder of a system. Have we heard of entropy before from like chemistry? Probably. Yeah. Okay, cool. All right. So I won't belabor that. We kind of know what entropy is. It's a measure of essentially chaos. And so in discussing this, we have what is called the Clausius inequality, which I'm kind of sad we're not closer to Christmas because I would call this the Santa Clausius inequality. I'm just kidding. I would only do that like once. So this inequality was first discovered by a German physicist named Clausius, who lived in the 1800s. And it states that for any thermodynamic cycle, we have that the integral over that cycle, so I'm going to write this as a path integral, of the differential change in heat transfer Q over T is less than or equal to 0. Okay, so for a cycle, this integral, this path integral, is equal to the integral from state 1 to 2, plus the integral from state 2 to 3, plus the integral from state 3 to 4, plus the integral from state 4 to 1. Okay, so if we were, for example, looking at a refrigeration cycle, you know, the path, these integrals would be over each of these processes going from state 1 to 2, 2 to 3, 3 to 4, and then from 4 back to 1. Okay. Couple of things to point out in this equation. So this term right here, delta Q, is the heat transfer at a part of the system boundary during a portion of the cycle. T is, of course, the temperature. And this is the absolute temperature, so that's important. At that part of the boundary. And then this path integral or cyclic integral like I mentioned, can be decomposed like this. Okay. All right, so in this equation, the equality holds for a reversible cycle. So what I mean by that is if you have this equation and you're applying it to a reversible cycle, you don't have the less than or equals to anymore, you just have equals. And then the inequality holds for an irreversible cycle. All right. So we can demonstrate this using the Kelvin-Planck statement of the second law. But before we do that, the Clausius inequality can be rewritten as an equality in the following way. So we can write this as the path integral of delta Q over T is equal to negative sigma for the cycle, where sigma for the cycle is then less than or equal to 0. So what this means is that sigma cycle is greater than or equal to 0. Okay, so this is just like a little bit of semantics. So we're just going to say that our integral is equal to this quantity, and the inequality is kind of buried into that quantity sigma. Okay. So sigma cycle can be viewed as representing the strength of the inequality. And for a reversible cycle, we have that sigma for the cycle is equal to 0 because the equality holds. And so this means that our integral of delta Q over T is equal to 0. And so I've put a little subscript rev on here. This means that it's for a reversible cycle. All right, for an irreversible cycle, then we just have the inequality. So sigma of this cycle is greater than 0, which then implies that our path integral of delta Q over T for an irreversible process is less than 0. All right, so now the subscript is indicating an irreversible process. Okay. Okay. So quick note, it's important to note that sigma for a cycle being less than 0 is impossible. That's because we cannot have a situation where our integral of partial Q over T is greater than 0. Okay. So that means that sigma cycle can also be viewed as a measure of the effect of irreversibilities present within the system that is executing the cycle. We're going to later interpret that as the entropy produced or generated by irreversibilities in the cycle. Okay. That was weird. Okay, so let's define entropy change now. So if you remember from, I think, topic 1, maybe, like at the very beginning of this class, we talked about the definition of a property. And when we were doing that, we said that any macroscopic characteristic of a system to which a numerical value can be assigned at a given time without knowledge of the history of the system, that's what a property is. Okay. So between any initial and final conditions, the change in the value of some property that I'm just going to call B is independent of the path followed. Or in other words, my integral from state 1 to state 2 of my property B is always going to be equal to B2 minus B1. So a specific example of this is the integral from 1 to 2 over volume is just the volume at 2 minus the volume at 1. Okay. So if we consider a property such as volume in an n-step cycle, what this is going to look like is the following. So we have our cyclic integral of volume is equal to the integral from 1 to 2 of dv plus the integral from 2 to 3 of dv. And then we keep going like this until we have the integral from state n minus 1 to state n of dv. And then last but not least, we need to go from state n back to state 1 because this is, of course, a cycle. So we need to get back to state 1. All right. And this is equal to the integral from 1 to 1, right, of dv, which is just v1 minus v1, which is 0. We're basically just saying you have to get back to where you started from. And so your overall change in that thing has to be nothing, right? So the integral of any property over a cycle is always equal to 0. Okay, but what about a non-property such as work? Or the work of heat? It is not necessarily 0. So if you remember, if we have a reversible cycle, the Clausius inequality states that we have this path integral of delta Q over T for a reversible cycle is equal to 0. And this is regardless of the process or the cycle that's been taken, as long as it's reversible. Okay. So this means if this integral is 0, then this must be a property, right? So Clausius realized, sorry, this should be realized, in 1865 that he had discovered a new thermodynamic property because of this. And he named it entropy, which originates from a Greek word, which I've typed out here, but I will not try to pronounce. But that word means transformation. Okay. Entropy change during an infinitesimal reversible process is related to the heat transfer and temperature as the following. So essentially this is how I'm going to write a capital S, okay? So this is equal to what we had as our integrand, so delta Q over T for a reversible process. All right, so we're just using the Clausius inequality to define what our infinitesimal change in entropy is for a reversible process. Okay. All right, and so if we have a reversible process that goes between states 1 and 2, then we have the following. So we have S2 minus S1 is equal to the integral between 1 and 2 of ds, which is equal to the integral from 1 to 2 of delta q over t, which is again reversible. I'll probably write this a bunch more times, but just remember t must be absolute. All right, so make sure you're using Kelvin or Rankine. All right, I already mentioned this, but that subscript rev is added to indicate that the integration is carried out for an internally reversible process that links states 1 and 2. Okay, so we've talked about the specific version of pretty much every property in this class. So we're going to talk about specific entropy as well. So specific entropy is, we're going to use the lowercase s symbol. So that's how I'm going to write a lowercase s. And it is just the total entropy divided by mass, how we always define specific properties. And the units for entropy is kilojoules per Kelvin or BTU per degree Rankine. And the units of specific entropy are kilojoule per Kelvin, kilojoule per kilogram Kelvin, or BTU per pound of mass, degree Rankine. Okay, so far so good? Okay, so since entropy is a property, the change of entropy or the change in entropy of a system in going from one state to another is the same for all processes, both reversible and irreversible between those two states. However, the integral of delta Q over T will give us the value of entropy change only if the integration is carried out along a reversible path between the two states. Okay, this is because the integral of delta Q over T is not a it's not a property for an irreversible process. Okay, so essentially, if we have an irreversible process, we can still figure out the entropy change, but we have to do it by performing the integration over some convenient imaginary reversible process. Between those two states. Okay. Fortunately for us, specific entropy data is tabulated. It's given relative to some reference state, and it can be retrieved just like all the other properties that we've used tabulated data for. So just like internal energy, specific volume, and enthalpy. All right, so we're going to be using tables again, but it will function all in the same way. We're just going to be looking at entropy. All right. Okay, so before we look at looking up entropy data in tables, we're first going to talk about entropy change for two special processes that go from states 1 to 2. So these are going to be common things that I would recommend committing these two things to memory. All right, so this will come up in other classes after this one as well. It's important. Okay, so the first one is a reversible isothermal process. If we have an isothermal process, what does that mean about temperature? I just hear, shh, thank you. It's constant. Great, perfect. All right, so let's look at what this looks like. So for our reversible process, we have that S2 minus S1 is the integral from 1 to 2 of delta Q over T for a reversible process. But we have that T is a constant. So does that mean that we can do anything special with it at this stage? Yeah, we can just take it out of the integral. So if it's a constant, we can just pull it out front. So we have 1 over T, integral from 1 to 2, dq over the reversible process, which just gives us, of course, Q for our process over T. And again, remember, this has to be absolute. Okay. If we have a reversible adiabatic process, does anybody know what adiabatic means? That's isobaric. No heat. Isochoric. What? No heat transfer. Yes, thank you. So great. So adiabatic is that Q is equal to 0. All right. So let's look at our reversible change in entropy. So we again have S2 minus S1 is equal to the integral from 1 to 2 of delta Q over T. So if Q is equal to 0, that means this whole thing is equal to 0. Okay? Which just means that S2 minus S1 is equal to 0, which is also a special kind of a process. Does anybody know what it's called? It's okay if you don't, I'm just curious. No? Okay, so this means that entropy does not change. And so when entropy doesn't change, we call this an isentropic process. So this is a process in which entropy is constant. Entropy. There we go. Okay, so I think in one way or another, we've mentioned all of kind of the very important vocabulary from this class, at least in my opinion. So isothermal, isobaric, isochoric, adiabatic, and isentropic. All right, so those are all good ones to, learn for this class, but you will need them in other classes beyond this as well. So they are important. Okay. All right. Now we are ready to talk about the Carnot cycle. So if you remember from the last unit, I brought up the Carnot cycle a bunch of times and said, but wait, there's more. We'll talk about it later. Now is that time. So Nicolas Sadi Carnot was a French military leader in the late 1700s and early 1800s. And he was among the first to study the principles of the second law of thermodynamics. And he was the very first to introduce the concept of cyclic operation. And in 1824, he conceptually devised a theoretical reversible cycle that's composed of 4 reversible processes, which include 2 isothermal and 2 adiabatic processes. All right, so 2 of these processes in his cycle are at constant temperature, and then 2 of them, Q is 0. Okay. This cycle is, of course, known as the Carnot cycle. And it can be either operated as a work-producing heat pump or a heat engine cycle, sorry. Or you can reverse the direction of the cycle, and that would give you a refrigeration cycle. All right, in either case, whether you're running it as a heat engine or as a refrigeration cycle, the Carnot cycle yields the maximum theoretical efficiency, or the COP, which we talked about last time, no matter which direction you are running it. Okay? Hopefully you can already answer this question based on what we talked about last time, but the Carnot cycle cannot be achieved in real life. This is a purely theoretical construct it's a completely idealized system. So we can't actually do this because it's composed of 4 reversible processes. Which I should have written over here, but there you go. Okay. All right, so the Carnot heat engine is composed of 4 reversible processes, and it operates between 2 temperatures. We're going to call them TL and TH, so low and high temperatures. The process from 1 to 2 is a reversible adiabatic compression. All right, and when we do this, temperature rises from TL to TH. All right, so since this is reversible, that means that we have S2 minus S1 is equal to the integral from 1 to 2 of delta Q over T for a reversible process. But since this is adiabatic, that means that dq is 0 and this is 0. Okay? So we have from this, our process from 1 to 2 means that S2 is equal to S1. So this is an isentropic process. Okay? All right, cool. Process 2, 3. So the way we get from state 2 to state 3 is through again, reversible, now isothermal process, or sorry, expansion, isothermal expansion at temperature TH. All right, heat input QH occurs during this process. All right, so again, we have a reversible process. So we have S2 minus S1 is equal to the integral from 2 to 3 of delta Q over T. And again, this is reversible. So since this is isothermal, that means that I can bring my 1 over T out to the front. So I have 1 over T integral from 2 to 3 delta Q over that reversible process is equal to, so our integral, we're already told QH is what's input into this from states 2 to 3. So our integral of dq just gives us Q23 over TH, which is just a positive QH over TH. I put this positive here because heat is input. So when we have an input of heat, that's positive. Okay. All right, so keep in mind that this means that our change in entropy is greater than 0. Okay. Okay, moving right along, our process to take us from state 3 to 4 is a reversible adiabatic expansion. And during this, our temperature is going to drop from TH to TL. All right, so again, we start off with our reversible difference in entropy equation. So we have, oops, these are not the right states. So we are going from 3 to 4. Oh, and I did it wrong over here, sorry. So this should be 3 minus 2, and then this is 4 minus 3. Sorry about that. All right, so here we have our integral from 3 to 4 of delta Q over T for our reversible process. And again, this is adiabatic. So that means that, again, our delta Q is 0. So this is also equal to 0. And it means that S4 is equal to S3. And this is an isentropic process as well. Okay. Finally, we have a process that's going to take us from state 4 back to state 1. And for this process, we have a reversible isothermal compression. All right, and this is going to happen at TL, and heat loss, QL, occurs during this process. All right, so if we have S1 minus S4 is equal to the integral from 4 to 1 of delta Q over T for our reversible process. This is again isothermal. So we're going to bring 1 over T out to the front. And then our integral of delta Q for our reversible process from 4 to 1 is going to give us Q41 over T, which is now minus QL over TL. All right, the minus sign is because heat is lost. All right, so this means that our change in entropy is less than 0. Does this feel okay to everybody so far? Okay, so we can draw this process on both a PV diagram as well as a TS diagram. So I will do that now. So here's our specific volume. So we've got volume over mass and then pressure on this side. If you remember from PV diagrams, we have lines for isothermal processes, right? So we're going to have 2 lines on here because we have 2 different temperatures that our cycle operates between. So we will have a curve for TH. So this is our isotherm line. And then we'll have another curve for TL. Okay. And we are starting and ending at our lower temperature. And we're also starting at a smaller specific volume than state 4. So this is roughly where state 1 will be. And then if you look at what happens between 1 and 2 is we have a reversible adiabatic compression. So we're compressing our working fluid, which means our specific volume will go down. And then we're also going from our lower temperature to our higher temperature. So we're going to jump up to this temperature when we go to state 2, and our specific volume will decrease. That makes sense? Okay. To go from 2 to 3, we're doing an isothermal expansion. So isothermal means we're going to stay on our isotherm line and we're expanding. So we're just going to move up in specific volume. Okay, so we'll move to over here where this is our specific volume at 3. All right, and during this process, we are inputting heat. So often this is done by drawing an arrow for the heat that's being added into the system. So pointing towards our cycle means that it's coming in. All right, and then going 3 to 4, we're doing a reversible adiabatic expansion, and our temperature is going to drop from TH to TL. All right, so we're expanding, which means our specific volume is going to increase again, and we're going to hop down to our lower isotherm line. Okay, so I need to draw this out a little more. So I'm going to go to here. So here is V4. And then this will curve like so. And then last but not least, we are doing a reversible isothermal compression to get from state 4 to state 1. Okay, so isothermal means that we are going to stay on our same isotherm line. And then since it's compressing, that means that our specific volume is going to decrease, which is good because our state 1 is obviously at a smaller specific volume than state 4. So we are just connecting 1 and 4 like so. All right, and heat loss is occurring here. So now we draw this as an arrow showing QL coming out. Does drawing this process on the PV diagram feel okay to everybody? Okay, cool. The TS diagram is quite a bit simpler. So we'll do that second. All right, so I'm going to have temperature on my vertical axis, and then I am going to have entropy, specific entropy. So this is S over M on my horizontal axis. And if we look at kind of our summary of these 4 processes, we notice that we have S1 and 2 are the same, and S3 and 4 are the same. So we only have 2 entropies that are unique in this process. So we have S1 is equal to S2, and we also have that S3 is equal to S4. All right, so we have 2 values, and then we also have 2 values of temperature. So we have a TH and a TL. All right, process 1 starts at TL, and we have S1. So that means that we're sitting right here. All right, when we go up to state 2, our temperature is rising to TH. So we move up to TH and our entropy is staying the same, right? So if we look at process 1, 2, S2 is equal to S1. So we just go in a straight line up from 1 to 2. All right. To get from 2 to 3, we're doing an isothermal expansion. All right, and we have that our entropy change S3 minus S2 is a positive number. So we're moving to the right along a constant temperature line. Too far. So here is 3. And again, we're having QH come in. So I will draw that here. To go from 3 to 4, we're dropping from TH to TL, but our entropy stays the same because this is isentropic. So that means we just go straight down to here. And this is state 4. And then last but not least, to go from state 4 back to state 1, we're doing an isothermal process where S1 minus S4 is a negative number. So that means we have to move to the left on that constant temperature line. Like so. And then again, we have QL coming out. Does that feel okay? Okay. Let's do a quick break unless there are questions, and then we'll come back and keep going. All right. Okay, so we are going to now look again at the entropy change equations. All right, so we have the following. So for our process that goes from state 1 to 2, we have S2 minus S1 is equal to 0. And I'm just replicating what we already figured out on the previous page. Okay, I'm not just making this up and skipping steps, just so you know. All right, and then to go from state 2 to 3, we have S3 minus S2 is equal to QH over TH. And then to go from state 3 to 4, we have S4 minus S3 is equal to 0. And then finally, to go from state 4 back to state 1, we have S1 minus S4 is equal to minus QL over TH. Oh, no, sorry, TL, sorry. Right? So what we're going to do is we are going to add all of these together. All right, and so when we do that, we get a bunch of things to cancel out, right? So we have S2 minus S2, we have S1 minus S1, we have S3 minus S3, and S4 minus S4, right? So all those terms go away. And then we also have on the right-hand side that QH over TH minus QL over TL is equal to 0. Okay, so what this means is that for a Carnot cycle only, we have that QH over QL is equal to TH over TL. All right, so let's use this fact that we just learned to talk a little bit more about how that kind of factors into the Carnot efficiency that we talked about in the last topic. All right, so if you remember, we had eta Carnot. So this is our efficiency that we talked about last time, is W net over Q in. All right, and we were able to write this as Q in minus Q out over Q in. Q in is QH and Q out is QL, right? So we have QH minus QL over QH. And this is 1 minus QL over QH. Right? But we also just showed that QH over QL is TL over TH. So we can substitute that in here, and we can also rewrite this as the following. So we can say this is also 1 minus TL over TH. And this is our thermodynamic maximum efficiency that we got before. All right, so that's how this all came to pass. Okay. So QH is our Q in and QL is our Q out. Okay. I think I already mentioned this before, but just to re-emphasize this. So if all the processes in the Carnot heat engine are reversed, so if you run in the counterclock direction, this cycle would operate as a refrigerator or a heat pump. Okay. Okay, All right, so now that we have all of that, we can talk about looking at entropy data for water as well as refrigerants. So we've already talked about looking up thermodynamic data in tables extensively in topic 3, which you are all experts on now. Specific entropy values are also in those tables. So you probably noticed that there were the lowercase s values in those same tables that we have been using before. That is specific entropy. So we are going to use those same tables again in the same way that we have used them for properties like specific volume, specific energy, and enthalpy. All right, and in addition, the same phase rules are going to apply. So for example, I'm going to just draw this on a TS diagram. All right, we still have our same vapor dome. And on that vapor dome, since this is a TS plot, we also have isobars that are going to look like this, just in the same way as they did before. So these are, this is P2 greater than P1. This is P1, so these are isobars or lines of constant pressure. On this curve, on the left-hand side, this is going to be our saturated fluid specific entropy for state 1 or for pressure 1. And then this point would be our saturated vapor specific entropy for pressure 1. All right. And so if we have that our entropy is less than or equal to SF, this means we have a compressed liquid. All right, so if this is the case, that means that we are hanging out over here in compressed liquid land. Is that specific entropy or? Oh, you're right, this should be specific. I mean, kind of both, but yes, I should have made these lowercase s's. There, that's better. Thank you. If we have that, and this should not have a, sorry, this should not have a less than, or the equality on there. It should just be if it's less than that. If it's equal to SF, then we're at a saturated liquid, right? We're just sitting on the line. Okay, let me re-highlight this again. All right, if our entropy is between or on SF or SG, then we are in the saturated liquid vapor regime. So that would be under the vapor dome. All right, so we would be in here. And then finally, if our entropy is greater than SG, then this is a superheated vapor. All right, so this is the same deal as what we had before when we were looking at internal energies and specific volumes and enthalpy, right? So we can use entropy to figure out the state of something just the same as we did this before, okay? So if we are in the mixture region, we're going to calculate our specific entropy using the quality, just like how we did before. So that looks like the following. So we have S is equal to SF plus the quality X times the difference between SG minus SF. So this is the same exact form of the equation like we had for internal energy and all that good stuff. Okay, For a compressed liquid, the value of entropy can be approximated using the saturated liquid value at a given, do we use pressure or temperature? We use temperature, right? So we're going to continue to do that. All right, so essentially this means that S for a compressed liquid is approximately SF at a given temperature. Okay, so really nothing has changed. We're just talking about entropy rather than the other properties. Okay. So there is a special diagram that is new to us now, and it is known as the Molière diagram, which the formatting got changed. Okay, so it says that it's to the right because it was meant to be on this page, but it slid to the other page. So I'm sorry. So it's on the next page. So when I'm going to scroll down in just a second, but when you look at that diagram, note the location of the critical point. So this figure is intended for evaluating properties at superheated vapor and two-phase liquid vapor mixtures. And liquid data is generally not shown on these types of figures. Okay, so here is the diagram. So our critical point is all the way down here. All right, so because it's way down there, that's why we're not showing any liquid information on this chart. So we're looking at everything in the green is a saturated vapor liquid mixture. And then everything in kind of the gray scale is superheated vapor. Okay. Okay. And then just keep in mind the axes on this. So we have enthalpy on the vertical axis, and then this is entropy, of course, on the horizontal. Okay. All right, so let's do an example and give some of this stuff a try. So we have 1 kilogram of water is going to undergo a reversible adiabatic process. At state 1, it is a saturated vapor at a pressure of 1 bar. And at state 2, it has a pressure of 3 bar. And we want to find the temperature at state 2. All right. Question? Okay. All right. So let's write down what we have. We have lots of good information in here. So we have information about states 1 and 2. So for state 1, we have the phase is saturated vapor. And the pressure is 1 bar, which is 100 kPa. Okay. Since we have saturated vapor, what's our quality? 1. Yes. Excellent. All right. And then at state 2, we have that so this is P1, sorry. P2 is equal to 3 bar, which is 300 kPa. And we want to find T2. We know that our process 1, 2 is reversible and it's adiabatic. Okay. So, oh, and then we have M is equal to 1 kilogram. Okay. So let's write down our conservation of energy. which is E2 minus E1 is equal to Q minus W. We also have a reversible process, so we can write down our statement of the Clausius inequality as the following. So we have S2 minus S1 is equal to the integral from 1 to 2 of delta Q over T for a reversible process. All right. And let's simplify this based on the information that we have. So first, we're given that this is reversible. So we're already using that equation. So that's good. But then we also are given that as adiabatic. So how do these equations get simplified because it's adiabatic? Right, so the Q's are 0. So this goes to 0, this goes to 0, which means that we have nothing given to us about work. So we're going to assume there's no work, right? Okay. So this means that S2 minus S1 is 0. And I'm also going to rewrite this in terms of specific entropy. So I can pull the mass out front and then have the specific entropy at 2 minus the specific entropy at 1. So this means we have an isentropic process. Right? Okay, so any ideas about what we should do first? Yes, great idea. So first, let's find our entropy at state 1. Any ideas on how we might do that? We are given pressure and we are given quality. Yes, we should use a table. So, which table? Based on the quality, which table should we use? Are you sure? So since we have a quality, even though it's at 1, we were on the vapor dome line, right? So we still will use our saturated vapor table. Yeah, so S1 is just going to be equal to SG because X is equal to 1. Does that make sense, everybody? Okay, so since X1 is equal to 1, that means that S1 is equal to SG at our P equals 100 kPa. All right. So let's find that in the table, which is here. Okay, so we're going to go to 100 kPa, which is here. And we are going to find SG, which is all the way over here. So we have 7.3589. Kilojoules per kilogram Kelvin. All right. And since this is an isentropic process, this is also the entropy at state 2. So since S1 equals S2, we also have the S2 is 7.3589 kilojoules per kilogram K. Okay, so step 3, we need to figure out some more information about state 2, right? So we need to first figure out what state we're at state 2. All right, so we will compare S2 to SF and SG at P2, which is 300 kPa. Right? So let's do that. So at 300 kPa, we have this line of data. So we are going to compare 1.6717 to 6.9917. So we have SF is 1.6717 kilojoules per kilogram Kelvin, and then SG is 6.9917 kilojoules per kilogram K. Okay, so where are we at? What S2 relates to this how? Yeah, so S2 is greater than SG. So what does that mean? Yeah, so we're in a superheated vapor. All right, so then we're gonna go to our superheated vapor table and we will figure out what the temperature is based on the entropy that we have and the pressure that we have, right? So use superheated vapor table to find T2 using S2 and P2. Okay, so we are going to go to the superheated vapor tables. We are at 300 kPa, which is 0.3 MPa. So we're going to look at this pressure cell here. All right, and I am just going to take a screenshot of this and move it over. So just remember that entropy is our very last column on this thing, okay? Okay, so here is our table. So for our pressure cell, we want to make a little interpolation table of temperature and entropy. So we know that our entropy is 7.3589. So we want to find two entries for temperature and entropy that are close to that. So one below and one above. And it looks like we should look at these two. So our lower one is 7.3132, and then our upper one is 7.5180. These are all kilojoules per kilogram Kelvin. And then our temperatures on those are 200 C T2, which we're going to find, and then 250 C. Right? So we will interpolate. So we have T2 minus 200 divided by 250 minus 200 is equal to 7.3589 minus 7.3132 divided by 7.180 minus 7.3132. And if we solve this for T, we get 211.2 degrees C. Okay? Is that okay? A variation on a theme of what we've done a million times before? Fantastic. Okay. Now let's talk about entropy change for an arbitrary process. So if we consider a cycle that's made up of two processes, so a process that goes from state 1 to state 2, which is an arbitrary process. So this means it could be reversible or irreversible. And then also a process 2-1, which is a reversible process. All right, so from the Clausius inequality, we have that the integral over this cycle is delta Q over T is less than or equal to 0 for a cycle. Or we could also write this as the integral from 1 to 2 of delta Q over T plus the integral from 2 to 1 of delta Q over T, which is reversible, is less than or equal to 0. All right, so what I'm saying here is that we have two states, 1 and 2, and we have a process that goes from 1 to 2. So this one could be reversible or irreversible. And then we also have a process, a different one, that goes from 2 to 1. And this one is reversible. Okay, so we can break out this cycle into these two steps. So going from, what have I done? Hang on. I drew 2 points for one. No. Okay. There, that's better. Okay. Okay, so we have our process that goes from state 1 to state 2. That's this guy. And then we also have our process that goes from 2 to 1, which is this guy. Right? And then those two things summed together, this whole sum is the same as this integral. Okay? Okay, so our second integral that is up here, so the one in yellow, that one is a reversible process, okay? And that was by design because we can rewrite this in terms of entropy change as the following. So we can say that the integral from 2 to 1 of delta Q over T for that reversible process is equal to S1 minus S2. Okay? So that means that our equation now becomes the integral from 1 to 2 of delta Q over T plus S1 minus S2 is less than or equal to 0. Now, keep in mind that if this term right here, it could be reversible or irreversible, right? So if this is reversible, then we have that S2 minus S1 is equal to the integral from 1 to 2 delta Q over T, reversible, right? And if it's irreversible, then we have S2 minus S1 is greater than the integral from 1 to 2 delta Q over T. Okay, so we can rearrange this equation then in the following way. So we can say that S2 minus S1 is greater than or equal to the integral from 1 to 2 delta Q over T. Or we can rewrite it as ds is greater than or equal to delta Q over T. Okay, so this equality holds for a reversible process. And the inequality holds, so inequality holds for an irreversible process. We can rearrange this equation to yield what's called the closed system energy balance. Or sorry, entropy balance. And so that looks like the following. So we have S2 minus S1 is equal to the integral from 1 to 2 delta Q over T plus S gen. All right, so S gen is always greater than or equal to 0. And that's this term here. So this is kind of the same idea as that sigma term that we had before. So we changed our inequality into a strict equality, and then we added this term that might be greater than or equal to 0. Okay. So just to kind of talk about these terms that exist in here real quick. So we have S2 minus S1, which is just our entropy change. During an arbitrary process. From state 1 to state 2. Our integral, this guy, this is our entropy transfer during our process 1, 2 due to heat transfer. And then this term here is entropy generation due to irreversibilities, due to irreversibilities during the process. 1, 2. Okay. A few things about S gen. So this is very similar to the sigma that we talked about before. So S gen equals 0 is a reversible process. S gen greater than 0 is irreversible. And S gen less than 0 is impossible. Okay, so you can never destroy entropy in this way, okay? Okay. So given this, it's notable to mention that S2 minus S1 can be positive or negative. The entropy of a system may increase, decrease, or remain the same, which means isentropic during a process. But S will always increase with heat input. That's because delta Q is always greater than 0. With heat loss, entropy can increase, decrease, or remain the same, but that depends on the magnitude of Q and S gen. Okay. For a reversible process with heat loss, I'm sorry, for a reversible process, S gen is equal to 0. So that means entropy decreases with heat loss. All right. If we have a reversible process with heat loss, then we have S2 minus S1 is equal to the integral from 1 to 2 of delta Q over T plus S gen. But S gen is 0 for reversible. So we end up with the integral from 1 to 2 delta Q over T is less than 0. So this means that S2 must be less than S1. All right, and just to remind you, heat loss means that delta Q is less than 0. Okay. Okay. There are a couple other forms of doing entropy balance for a closed system. One of them is the following. So we are going to do this to kind of formulate this in different ways because it's usually convenient for different types of system analysis. All right. So for example, if heat transfer occurs at multiple locations along the boundary, and if the temperatures at these locations are uniform, then the entropy transfer term due to heat transfer can be expressed as the following. So we can say that S2 minus S1 is equal to the integral from 1 to 2 of delta Q over T over the boundary plus S gen. But since we're saying that the temperature is uniform at those different boundary locations, we can get away with turning our integral into a sum instead. All right, because we're integrating over a constant thing, so that would just be a sum. All right, so we can say that this is just the sum of the heat transfer at boundary location I divided by the temperature at boundary location I plus S gen. Okay, so this means that we have S2 minus S1 is equal to Q1 over TB1 plus Q2 over TB2, and so on and so forth, all the way up to Qn over TBn plus S gen. All right, so what we have here is essentially a system, and we have a bunch of little boundaries where different things are happening. So if that's our little boundary 1, then maybe we have boundary 2, and so on and so forth, all the way up to the nth boundary, this guy. And so what we have here is we have a temperature and a heat transfer at these different locations. So this is TB1, this is TB2 and Q2. And then maybe we have a third one. And then I'll just call this the nth one. But we could have as many of these as our heart's desire. Okay, so we can just sum them up in this way. We can also use this or express this equation on a time rate basis. As the following. So we can say that the time rate of change of the entropy is equal to the sum over all of the boundaries from I equals 1 to n. Actually, I need to fix this one too. So this is I equals 1 to n. All right, of q dot I over tbi plus s dot gen. All right, so this dot is a time derivative. All right. So what we have here is, this is time rate of change of entropy. We have our this term here is our time rate of change of entropy transfer due to heat transfer through the boundary. And then this S dot gen is the time rate of entropy production. Due to irreversibilities. All right. And just like the non-rate version, S dot gen has to be greater than or equal to 0. Okay. Okay, I'm going to end right here and we'll start off with an example next time.